You hear it all the time, right? Hydrogen is the future. It's the perfect carbon-free fuel that burns into nothing but water. So why aren't we using it everywhere? Well, the answer isn't just about making it. It's a really fascinating scientific puzzle that has to do with the surprisingly wild physics of fire itself. So here's how we're going to break this down. We'll start with that big promise of hydrogen, then we'll get into the two basic ways you can burn any fuel. From there, we'll tackle a really dangerous problem called flashback. Then we're going to go even deeper and uncover a strange microscopic behavior that changes everything. And finally, we'll see the amazing new tools scientists are using to tame this new kind of fire. I mean, the appeal is super clear, right? Hydrogen is literally the most common thing in the universe. You burn it with oxygen, you get a ton of energy, and the only thing left over is water. It's the clean energy dream, the key to a future without carbon emissions. Which brings us right back to that big question. If it's so great, what's the holdup? Now, you might have heard about the challenges of making so-called green hydrogen cheaply and at a huge scale. And those are real. But that's not the whole story. There's another roadblock people don't talk about nearly as much. And this is the real kicker. The bottleneck isn't just about making the fuel. It's about burning it. The actual act of combusting hydrogen, especially in the high-performance engines and turbines we need, is just incredibly tricky. It's full of problems that we just don't see with traditional fuels, like natural gas. To really get why it's so hard, we need a quick crash course on flames. It turns out there are really two basic ways to burn something, and this difference is everything when it comes to understanding hydrogen. So first, you've got diffusion flames. Just think of a candle. The wax vapor, the fuel, and the air around it are all mixing together at the very same time that they're burning. Then you have premixed flames. This is what's going on inside your car's engine or a big power turbine. The fuel and the air get mixed up really carefully before they ever get to the spark plug. Now, this premixed way is way more efficient, but you'll see in a second, it's also where hydrogen starts to cause all the trouble. This sensitivity is a huge headache for engineers. Just look at this chart. It's kind of wild. See the bar on the left? With a burner lip that's just 0.04 millimeters thick, that's thinner than your hair, the flame just blows out if the air hits 10 meters per second. But now get this. You make that lip a little thicker, just under a millimeter, and suddenly the flame holds on all the way up to 85 meters per second. That's an 8 times more stable flame from a change you can barely even see. Okay, so let's jump over to those pre-mixed flames, the efficient ones we want to use for power. This is where we run into the first big and, frankly, pretty dangerous problem with hydrogen. It's a phenomenon called flashback. Flashback is exactly what it sounds like. Hydrogen burns unbelievably fast, so fast that the flame can actually travel backwards against the flow of fuel and go right back into the delicate machinery that's supposed to be mixing the fuel and air. This is bad, like destroy a multi-million-dollar turbine bad. It's a massive safety failure that engineers have to prevent no matter what. And this is what makes it so frustrating for engineers. Check out this table. On the top line, with 100% methane, that's natural gas, the flashback risk is low. That's great. But now look at the bottom row. When you mix in 50% hydrogen, you get a cool benefit. The flame is more stable, so you can run on less fuel. But the flashback risk goes way up. So the very thing that helps you be more efficient also makes the whole system way more dangerous. It's a really tough spot to be in. Now, flashback is a huge problem, for sure. But it's really just a symptom of something much deeper, something more fundamental. And this is where things get really weird. It all comes down to an invisible property of hydrogen that actually changes the physics of the flame itself. Okay, think of it like this. Imagine you're trying to mix a big crowd of people together for a group photo. You've got some slow-moving folks, and you've got a couple of super fast, nimble people. Let's call them escape artists. Before you can even get everyone in place and say cheese, those escape artists have already wiggled through the crowd and are out on the edges. Well, in our flame, hydrogen is that escape artist. So that escape artist effect, it has a scientific name, differential diffusion. Because hydrogen molecules are so incredibly light and zippy, they just spread out way faster than the heavier methane and air molecules they're mixed with.
So remember that perfectly prepared fuel-air mix we wanted? Well, differential diffusion messes it all up on a microscopic level, right at the last second before it burns. The fuel you think you're burning isn't the fuel that's actually burning.
So what does this actually do to the flame? Okay, let's look at the structure of a normal methane flame, like inside an engine. A flame has two parts, a really thin reaction zone where all the chemistry is happening, and a much thicker preheat zone in front of it that warms everything up. You can see here, with just methane, that preheat zone is about 6 times thicker than the reaction zone. Pretty straightforward. All right, now here's the mind-bending part. Let's add 60% hydrogen to the mix. Those zippy little hydrogen escape artists diffuse away from the curved parts of the flame, and they take their energy with them. And look what happens. The preheat zone gets dramatically thinner. It drops from being 6 times thicker than the reaction zone all the way down to just 3 times thicker. This completely changes how the flame behaves, its speed, its stability, in ways that are just incredibly hard to predict with old models. So now we're stuck with this invisible, totally counterintuitive physics happening inside a chaotic, turbulent explosion. If we're ever going to engineer our way around this, we first have to understand it. And that's where some really cutting-edge science comes into play. So how do you even do that? I mean, really, how do you study what's going on inside a fire that's hotter than lava and more turbulent than a hurricane? You can't exactly stick a probe in there. The answer is you build a virtual flame inside a supercomputer. Scientists use these incredible computer models to see the invisible dance of the molecules. One of the key methods is called MMC, and you can think of it like a race with a staggered start. The model sorts all the molecules by speed. It knows hydrogen is the fastest runner, so it lets it start mixing first. Then, a split second later, it lets the next fastest molecules start, and so on, all the way down to the slowest ones. By creating this staggered start inside the computer, the model can finally accurately predict how those escape artists change the fuel mix right at the flame. And the results are an absolute game changer. Just look at this table. The older models, they could kind of guess at how the fuel might generally even out over time, but they totally failed to predict how the hydrogen would separate itself from the other fuels, what scientists call the decorrelation rate. The new MMC models, there on the bottom row, they predict both. For the first time, engineers have a tool that can actually see what the fire is doing. Okay, let's zoom back out. We went from the big picture of clean energy all the way down to the microscopic physics of a single flame front. Now we can see how this incredibly deep science is the key to actually building that clean energy future.
All right, so what have we learned? Let's just boil it down. First, burning hydrogen is not simple. It's super sensitive to microscopic details. Second, you've got this dangerous trade-off between keeping the flame lit and preventing a catastrophic flashback. Third, the real root of the problem is differential diffusion, hydrogen's weird ability to change the flame it's supposed to be fueling. And finally, these new computer models are absolutely essential. They're the tools we need to understand all this and engineer the solutions of the future.
So while we often think about the hydrogen economy in terms of big pipelines and massive production plants, the real work, the breakthroughs, are happening right now, inside supercomputers that are modeling the beautiful, chaotic physics of a single flame. The path to green power doesn't just run through a factory, it runs through the fire itself. So the real question isn't whether hydrogen is the perfect fuel, it's whether we're smart enough to finally figure out how to burn it.